Good morning, good afternoon, wherever you may be in your day. Welcome to another video where we will use the letter Q. Okay, so last time we talked about a pure substance. Now we're going to get into that chemical reaction with a pure substance, and then not to tease the next video, but we'll do where we put them all together with the whole idea of a apparatus or an object for measuring heat flow. Okay, phase changes. Let me define two terms for you. Heat diffusion. Heat diffusion is probably what it sounds like. It's the heat change associated with fusing something together or going from a liquid to a solid or solid to liquid. So it's changing between the solid phase and the liquid phase. And how much energy does that take? So if we're melting, we put energy in because liquids have more energy than solids, or liquids are at a higher temperature than solid, which is a measure of their general energy. And if we freeze something, this is counterintuitive, but when the chemical freezes, it gives off heat because it's going from a high energy state, which is a liquid, to a low energy state, which is a solid. That energy has to go somewhere. We can't create or destroy matter. So freezing is exothermic and gives off heat. Melting is endothermic and it takes energy to melt. That makes more sense. Sometimes we don't think about this idea of freezing giving off heat. So just think about, higher gases, liquids, solids. And the energy's got to go somewhere. Against the chemicals we care about, not us. It's very sad, I know. I like to think about I love my ergocentric universe. I don't know why anyone wouldn't. But, nevertheless, we're in chemistry class, so we care about the chemicals. Okay. So, what's our symbol for heat diffusion? Delta H fusion. So, remember the first video where I apologized to all the physics people and I said I was going to do some hand waving? I'm going to do some hand waving. When we talk about Q of a chemical reaction, that's delta H. I know. I apologize for anyone that knows any science. This is enthalpy. And we're just going to really view that term as heat of a chemical reaction or heat of chemicals. And I'm going to keep it that simple. Read the book. There's a much better description. There's some real physics, thermodynamics, chemistry going on behind the scenes. But for keeping things simple, this is our Q in chemistry. If it's a chemical reaction and it's a Q, we call it delta H. And it's typically kilojoules per mole, almost always. Okay, so heat of vaporization is the same thing. This is solid to liquid, so this is liquid to gas. In either direction, we put energy in to boil something, to vaporize something. Energy comes off when it condenses, precipitates, whatever you want to view the other direction as. And again, delta HV, or sometimes VAP for vapor. And this is F sometimes, or FUS, or sometimes write out the whole word. If you see an F, it's fusion. See a V is vaporization. Think fusion, think the solid end of the changing phases, and vapor, think the gas end. Liquid's always in the middle. So it's part of both of them. And then, so this is going to be what I call Q of a reaction. So it's going to be, and look at our units. We got energy, we got Q on top, and we got Q divided by our moles. So again, swing that over, make the math work, and now we have what? Q equals N times our given vaporization energy or fusion energy. So Q of a chemical reaction is going to just be the moles times the enthalpy change, or standard enthalpy change. And again, these are going to be in kilojoules. All the ones we did before with the little c are in joules. So just remember, if you're combining them together, either change all the kilojoules to joules or change all the joules to kilojoules, but make sure they match. Okay. So part of me wanted to do this in like 3 boards and slowly roll it out so you're listening to me and not looking at everything up here. But I literally just went over my freezer and looked at the temperature. The temperature of my freezer at home is minus 19 degrees Celsius. I also looked up the temperature it takes to sterilize an object using steam. Sterilization process begins at 115 degrees Celsius, so autoclaves, things like that. So my question is, what would have to happen to go from an ice cube to sterilizing steam? And what would happen as we heated up that ice cube? Well, as we first put energy into the ice cube, it's going to look exactly the same. But we would notice that the ice would change from minus 19 degrees Celsius. It would go to minus 18, minus 17, minus 16, minus 15, all the way until it got to 0 degrees Celsius. Still be a solid, still look, as icy as ever, and give off that heat. Absorb that heat. Once it got to 0 degrees Celsius, this is the melting point, or freezing point, depending on point of view, of water. So at this point, it starts to melt. It does not actually change temperature until all of the ice melts. So if you have a bunch of ice in a drink, you know, essentially your drink is at 0 degrees Celsius. If it was anything else, the ice would be gone. So all of the energy being absorbed from the atmosphere, from your hand, from the cup at the restaurant, is going towards melting the ice. It's not going towards heating the beverage. So your beverage stays nice and cold and consistently cold as long as there's ice floating in it. Now there is a little bit of equilibrium when the ice first gets dumped in, but once it's sitting on the table, your drink's the exact same temperature the whole time, as long as there's ice in it. Okay, so it's 0 degrees, and it's actually melting. Once it melts, we can raise the temperature again up until we hit the boiling point. And same idea with the boiling. This is why when you're cooking, a lot of times they'll say just boil the water. They don't really talk about heavy boil, low boil, simmer. They're all really the same. You're at the same temperature. Now, a simmer is better than boiling water going all over your kitchen. I mean, that's a mess and it's a danger hazard. So it's always nice to do a very, very gentle boil. But as far as the temperature goes in cooking the food, boil away. And then once we have boiled all the water, it's all in the gas phase, we can shift it up to the next temperature. So there's 5 actual transitions here, and each of these has to be mathematically individually dealt with. So if we're looking at ice going from negative 19 to 0, that's just heating of a pure substance. So that's Q equals Cm delta T. If we're looking at this, 0 degrees to 0 degrees, obviously there's no delta T. This is a chemical reaction, so chemical reaction is going to be Q equals N delta H. In this case, I've made it more specific and said fusion. Now we have our liquid water, and we raise the temperature. We're back to a pure substance, and we're back to changing the temperature. It's Cm delta T. And I will point out that ice absorbs heat differently than water, which absorbs heat different than steam. So these are going to actually be different C's. One for ice, one for water, one for steam. Make sure you grab the right one. Once again, now we have no temperature change. So this is a chemical reaction. So it's N delta H. And again, I was specific and put vaporization, but really just N delta H. And then this last part, we're moving temperature again, pure substance, so Cm delta T. So you're going to see these same things over and over again, used in a different variety of ways. A lot like we do Stoic. Really, in that chapter, we only use 3 things, but we use them every way possible. So once again, we're really only using 3 Qs here, but we use them in a lot of different ways, so we really have to think about what they mean and what's appropriate. So, what would a problem... Oh, no, I got excited. Just very quickly, what does a heating curve look like? Then we'll do an example of this. Of what we just looked at is if we add heat at a equal interval, or if we want, so this could be time or heat added, and then our temperature change on the y-axis. You would see the temperature go up as we add heat, then it will be flat. So again, I just really want to emphasize this idea that a lot of energy goes into changing phases without affecting the temperature at all. And again, heat is different than temperature. Temperature is the average kinetic energy, where heat is looking at all of the electrons and all of the motion. It's the sum of all of the motion with that, as opposed to the temperature is the whole thing moving through space, where heat is all of the movements, the electrons and the bonds and the vibrations and all of those things. So subtle but different. Related, of course, but they are not the same thing. So it goes up, flat, no temperature change as we change phase, goes up again, and these slopes are different. These slopes have to do with the heat capacity. And it takes a lot more energy to boil something than it does to melt or freeze something. So again, I wanted to point that out visually. I think that's easy to see here. So this is what's going on graphically, your standard heating curve. And typically, I'm not going to give you a problem where you have to do all 5 parts. Seems overkill, to be honest. Here's a kind of bite-sized problem that if you can do this, you can do the whole thing. So let's take a look at this bite-sized problem. Calculate the energy needed to melt a 10-gram piece of ice at minus 5 degrees Celsius. Pretty straightforward. So, our giveaway here is we're changing temperature, and there's a phase change. Those are the 2 things we're really looking at here. So when you see this phase change, temperature change, I want you to map it out before you do any math. So, what do I mean by map it out? Like what I had on 2 slides ago. So we have minus 5 degrees Celsius, and this is a solid. We need to go to 0 degrees Celsius as a solid. Then we need to go from a solid to a liquid. And that's it, right? And then we've done what they've asked us to do. So this is a 2-step process. Step 1, step 2. Or I might even call that my answer. So again, map this out. Might be 1 step, might be 2, might be 3, might be 4, might be 5. More than likely it's probably like 2, 3, or 4. 5 seems overkill, 1's not enough, so, realistically from a testing standpoint, 2, 3, 4, something like that. But map it out, see what you have, and do that. So if I did this first part, we're changing temperature, so that's Cm delta T. The second part, we're changing phases, so that's N delta H. And now the question is, can I look up the right symbol? So here is everything that might be given to you, and I like to give you extra information on this. Make sure that you pick out what you need. So I had the capacity of ice, water, and steam. I have heat of fusion, heat of vaporization as I looked them up. So this first part's obviously ice, so let's use that one. Depending on your source, you might get 2.05, 2.06 joule per gram degree Celsius. My mass is 10 grams. Grams and grams, they match. Good. Double check. Always double check. 10 grams. And my change in temperature is 0 minus 5 or 5. Second part is moles. Oh my goodness. I don't have moles. I got 10 grams. What am I going to do? Well, first of all, if all else fails, convert everything to moles. So this is like second nature. Grams of water to moles of water. So that's not so bad. .555 moles. Once you have that conversion, we can put that here. And then we can just use this right here. Heat of fusion. 6.02. Oh, it's kilojoules. Let's make them both joules. I'm just going to multiply by 1,000. So multiply by 1,000 joules in a kilojoule. Drop that down here. And now all we have to do is hit a couple buttons on our calculator and we're all done with this video. Very exciting, I know. And I get 3,400... Oh, where are my safe figs? 3,440 joules needed, added, absorbed. Plus, whatever you want to put in there. That's all I got for you, folks. Have a wonderful day.